This is Venus, the planet that died. 108 million kilometers from the Sun, just a stone's throw away from Earth, lies a world that should have mirrored our own. Nearly identical in size, mass, and density, it emerged from the same primordial cloud of gas and dust, birthed in the same region of the solar nebula, and at roughly the same time. If you were an alien astronomer peering into the young solar system 4 billion years ago, you would have spotted two almost indistinguishable rocky planets dancing in the habitable zone of a tranquil yellow star. You might have anticipated their evolution to unfold in parallel. You might have envisioned oceans gracing both surfaces, but one of them would defy your expectations. Today, Venus stands as the closest thing to hell within our solar system, with surface temperatures averaging a staggering 462 degrees Celsius, hotter than lead melts, hotter than zinc, even hotter than many industrial furnaces. It is a world of extremes. This searing heat isn't merely a consequence of its proximity to the Sun. Mercury, which orbits twice as close, is comparatively cooler. Venus's inferno is fueled by its atmosphere, a suffocating shroud of carbon dioxide 90 times denser than Earth's atmosphere at sea level, exerting pressure akin to that found 900 meters beneath the ocean's surface. Thick clouds of sulfuric acid envelop the planet in an unyielding veil. No sunlight pierces through to the surface. From the ground, the sky glows with a dull, oppressive orange hue. The air is so dense that it bends light like water, warping the horizon into bizarre, distorted shapes. And the temperature remains relentlessly uniform. At the equator, the poles, on the sunlit side and the dark side. There are no seasons. There is no respite. This is a planet that has perished, and its demise is rooted in something chillingly familiar. The force that transformed Venus into a blazing furnace is the greenhouse effect, the same natural phenomenon that warms Earth's surface to life-sustaining temperatures. The same process that is now, gradually and measurably, warming our own planet. On Venus, the greenhouse effect spiraled out of control. It became an unstoppable force. The outcome was the total and irreversible annihilation of the planet's habitability. Yet, what elevates Venus's tale beyond a mere cautionary narrative is the tantalizing evidence, indirect, debated, but enduring, that Venus once cradled oceans. For perhaps the first 2 billion years of its existence, it was a world adorned with liquid water, where temperatures may have been conducive to life, and clouds reflected just enough sunlight to maintain a temperate climate. There lingers a possibility, extraordinary, unproven, yet not dismissed, that life might still thrive there. Not on the hellish surface, but high in the atmosphere, within the relatively temperate cloud layer, 48 to 60 kilometers above the ground, where conditions are mild, pressure is Earth-like, and something is producing a gas that, on our planet, is predominantly generated by living organisms. Tonight, we embark on a journey to trace the demise of a world, from its inception as Earth's twin to its transformation into a furnace, from the oceans it may have lost to the enigmatic chemistry it cannot elucidate, from the Soviet landers that endured mere minutes on its surface before succumbing to crushing heat, to the new wave of missions set to return to Venus in the 2030s, aiming to unravel the mystery that has haunted planetary science for decades. What went awry? For Venus is not just a lifeless planet, it serves as a warning, and that warning is directed at us. Be sure to subscribe, as there are countless more extraordinary cosmic tales waiting to be uncovered. For much of human history, Venus has been a dazzling enigma, a celestial jewel illuminating our night sky. It shines as the brightest object after the moon, casting shadows on the darkest nights and occasionally leading airline pilots to mistake it for an approaching aircraft. The ancient Romans honored it as the goddess of love and beauty, while the Babylonians referred to it as Ishtar. The Maya meticulously tracked its movements, intricately weaving its cycles into their calendar. To the naked eye, Venus appears as a brilliant point of white light, gracefully positioned near the horizon at dusk or dawn. The evening star and the morning star, once believed to be two distinct entities. Yet, beneath this radiant exterior lay a shrouded reality. Venus is perpetually cloaked in mystery. Its dense atmosphere reflects around 75% of incoming sunlight, rendering it extraordinarily bright but entirely opaque. No telescope on Earth has ever captured the surface of Venus in visible light. In the early 20th century, astronomers could only speculate about what lurked beneath the clouds. Many envisioned a warm, swampy world, perhaps a younger Earth adorned with tropical jungles and primitive life. Science fiction writers populated Venus with lush forests, vast oceans, and exotic civilizations. But when the truth finally emerged, it was harsh. As the space age dawned in the 1960s, the first measurements of Venus's surface temperature were obtained, not from spacecraft, but through ground-based radio telescopes. Unlike visible light, radio waves can penetrate Venus's thick cloud cover. When astronomers directed radio telescopes at Venus and measured the thermal emissions from its surface, they discovered temperatures far beyond expectations. The surface was scorching, hundreds of degrees hot. The envisioned tropical paradise was revealed to be a furnace. The Soviet Union, prioritizing Venus in its planetary exploration agenda, launched the first spacecraft aimed at entering its atmosphere. The initial Venera missions, Venera 1 through Venera 3, encountered various technical failures. However, Venera 4, launched in 1967, became the first spacecraft to successfully transmit data from another planet's atmosphere. It recorded temperatures soaring past 260 degrees Celsius before contact was lost, likely around 25 kilometers above the surface. Soviet scientists initially claimed a successful landing, but subsequent analysis revealed that the probe had succumbed to heat and pressure long before it reached the ground. The atmospheric pressure on Venus was far greater than anyone had anticipated. Early estimates suggested it might be about 20 times that of Earth's surface pressure, but the actual figure was closer to 90. Each subsequent Venera mission revised these numbers upward, unveiling an atmosphere that was not merely thick, but crushingly dense. The air on Venus is so heavy that it behaves almost like a liquid near the surface. Walking through it, if such a feat were possible, would feel less like traversing air and more akin to wading through warm water. Venera 7, launched in 1970, marked the first human-made object to successfully land on another planet and transmit data from its surface. It endured for 23 minutes on the ground, recording a surface temperature of approximately 475 degrees Celsius and a pressure of 90 atmospheres, before its batteries drained and the heat obliterated its electronics. It toppled during landing, which compromised its signal, yet the data it relayed was unmistakable. Venus was revealed as a hostile, barren world. However, the true images of this alien landscape would not emerge until later. In 1975, Venera 9 became the first spacecraft to return photographs from the surface of another planet. The image, a single panoramic scan, black and white, grainy by today's standards, depicted a terrain of angular rocks scattered across a flat, desolate surface, illuminated by the diffuse, orange glow of sunlight filtering through the thick atmosphere. There were no plants, no water, no signs of erosion by liquid, just rock, heat, and overwhelming pressure. The images captured by Venera 13 and 14, which touched down on the surface of Venus in 1982, were nothing short of breathtaking. Venera 13 delivered the first color photographs from Venus's surface, revealing a landscape of flat, layered rocks in vibrant shades of orange and brown, stretching toward a close, hazy horizon beneath a yellowish sky. This remarkable lander outlasted its intended operational time, surviving for 127 minutes, almost 4 times its designed lifespan of 32 minutes, before succumbing to the intense heat. In those fleeting moments, it drilled into the surface, analyzed soil samples, recorded the sound of the Venusian winds, and transmitted 2 panoramic images that remain the highest quality photographs ever taken from Venus's surface. Since 1985, no spacecraft has landed on Venus, leaving the surface unphotographed for over 40 years. Our understanding of the ground-level reality of Venus, its rocks, soil, sounds, and light, stems from a handful of Soviet landers that operated for mere minutes or hours before being destroyed. Astonishingly, the surface of our closest planetary neighbor remains one of the least explored regions in the solar system. We possess more detailed maps of distant Pluto than we do of Venus's terrain. Yet, what those Soviet landers unveiled during their brief existence was remarkable. The rocks at the Venera 9 landing site were angular and sharp-edged, scattered across a slope, indicating relatively recent fracturing, possibly due to volcanic or tectonic activity. The Venera 10 site, located 2,000 kilometers to the south, showcased a smoother landscape with flat, layered rocks that resembled sedimentary formations. Venera 13 discovered basaltic rock akin to the volcanic material found on Earth's ocean floors. Meanwhile, Venera 14, landing 950 kilometers away, identified a different type of basalt, tholeiitic, also oceanic in nature. These findings provide tantalizing clues. Basalt requires heat and melting to form, and its presence across multiple landing sites suggests that Venus has experienced volcanic activity in its relatively recent geological history. However, the Soviet landers sampled only a few locations on a planet with a surface area of 460 million square kilometers. Imagine attempting to grasp Earth's geology from just 4 photographs taken at random locations, each lasting only a few minutes. This illustrates our current understanding of Venus's surface. Venera 13 was also equipped with a microphone, capturing the sound of Venus, the first audio ever recorded from the surface of another planet. The sound was a low, steady hiss, the result of dense, hot air moving slowly across a barren expanse. Surface winds on Venus are gentle, averaging only about 0.3 to 0.5 meters per second, barely a whisper by Earth standards. Yet, the thick atmosphere means that even these subtle winds possess considerable force, akin to the flow of a slow river on our planet. The color of the Venusian landscape, as portrayed by Venera 13's cameras, is a striking palette of burnt orange and sienna. The rocks appear dark and slightly weathered, while the soil is fine-grained. The horizon is deceptively close, closer than on Earth, due to Venus's slightly smaller size and the way its dense atmosphere bends light downward, extending the visible horizon. However, the haze restricts visibility to just a few kilometers at most. You find yourself standing in a vast, sweltering, orange-lit cavern of air, perceiving only a small circle of ground around you, acutely aware that beyond the haze lies an entire world hidden from view. To comprehend how Venus evolved into its current state, we must journey back to the very beginning, the formation of the inner solar system, approximately 4.5 billion years ago, when the Sun was young and the planets were still coalescing from the remnants of the solar nebula. Venus and Earth emerged from the same cosmic neighborhood, birthed from a similar blend of materials, silicates, iron, nickel, and volatile compounds delivered by the relentless impacts of asteroids and comets. Their sizes are strikingly comparable. Venus boasts a diameter of 12,104 kilometers, while Earth measures 12,742 kilometers, marking a mere 5% difference. In terms of mass, Venus is about 82% as hefty as Earth. If you were to craft a planet as a replica of Earth, Venus would serve as an impressive first draft. In the nascent solar system, before their atmospheres began to diverge, before water evaporated away, and before carbon rearranged itself, These two planets were as close to identical as nature permits. They formed from adjacent rings of the protoplanetary disk, separated by just a few tens of millions of kilometers, a trivial distance on the grand scale of the solar system. They accreted at similar rates, achieved comparable sizes, and endured similar bombardments from the leftover debris of planetary formation. Both planets were almost certainly cloaked in oceans of magma shortly after their formation, molten surfaces extending thousands of kilometers deep, sustained by the immense energy released during accretion and the insulating effect of thick, primordial atmospheres rich in steam and carbon dioxide. Over millions of years, both worlds would have cooled, solidifying their magma oceans and condensing their atmospheres. And it is here, perhaps, that their paths began to diverge. On Earth, the cooling progressed sufficiently for water vapor to condense and rain down from the atmosphere, giving rise to the first oceans. With liquid water present on the surface, the carbonate-silicate cycle could commence, extracting carbon dioxide from the atmosphere and sequestering it in rocks. The atmosphere thinned, the greenhouse effect weakened, and the surface cooled further, paving the way for a stable, habitable climate. In contrast, Venus, being closer to the Sun and receiving more solar energy, may not have cooled as effectively. Its magma ocean might have lingered longer, and its atmosphere may have remained too hot and dense for water to condense. In the most pessimistic scenarios, Venus may never have possessed surface oceans at all. It was born hot and remained so. In more optimistic scenarios, it cooled enough for oceans to form. But the window of habitability eventually closed as the Sun brightened. Determining which scenario is accurate remains one of the most pressing questions in planetary science. Yet, from the very beginning, there was one crucial difference: distance from the Sun. Venus orbits at approximately 108 million kilometers from the Sun, while Earth orbits at 150 million kilometers. This difference, about 42 million kilometers, or roughly 28% closer, might appear modest. However, in terms of solar energy received, it is significant. Venus absorbs about 1.9 times the solar radiation that Earth does. When the planets were young, this difference was less pronounced. The young Sun was about 25 to 30% dimmer than it is today, a phenomenon known as the faint young Sun paradox. Yet, even with a dimmer Sun, Venus was warmer than Earth. As the Sun gradually brightened over billions of years, that warmth became a harbinger of doom. At its core, the tale of Venus's demise is a narrative about water. In the early solar system, both Venus and Earth likely received similar amounts of water, delivered by comets, water-rich asteroids, and the very rocks from which they formed. Climate models suggest that early Venus, under a fainter Sun and with adequate cloud cover, could have sustained liquid water on its surface for 1 to 2 billion years. Some models depict shallow oceans, while others envision something akin to a water world. The precise depth and extent of Venus's ancient oceans remain uncertain, but the chemical evidence of their existence is etched in its atmosphere. The pivotal evidence in this cosmic mystery is deuterium. Deuterium, a heavy isotope of hydrogen, is essentially a hydrogen atom with an additional neutron, making it nearly twice as heavy as its ordinary counterpart. When water molecules in a planet's atmosphere are bombarded by ultraviolet radiation, they can be split apart, dissociated, into their fundamental hydrogen and oxygen atoms. The lighter, regular hydrogen atoms tend to escape into the void of space, whisked away by the solar wind or propelled by their own thermal energy. In contrast, the heftier deuterium atoms, being significantly more massive, are more likely to be retained by the planet's gravitational pull. Over the course of billions of years, this selective escape enriches the atmosphere with deuterium in relation to hydrogen. The deuterium-to-hydrogen ratio, the D/H ratio, serves as a forensic marker for water loss. The greater the volume of water a planet has shed, the higher the D/H ratio in the remaining atmospheric water vapor. On Venus, The D/H ratio is astonishing. Observations from the Pioneer Venus orbiter in the early 1980s revealed that the atmosphere of Venus is enriched in deuterium by a staggering factor of approximately 100 to 150 times that of Earth's oceans. More recent findings from the European Space Agency's Venus Express mission, which orbited Venus from 2006 to 2014, indicated that this enrichment escalates dramatically with altitude, reaching ratios between 200 and 1,500 times that of Earth at elevations of 65 to 110 kilometers. This extreme enrichment serves as a compelling indicator, suggesting that Venus once harbored an abundance of water far exceeding what remains today, and that the hydrogen component of that water has been escaping into space for eons. The volume of water implied by the DH ratio is considerable. Some estimates propose that Venus may have once possessed enough water to envelop its entire surface to a depth of several hundred meters, perhaps even 3 kilometers deep. An ocean, a genuine liquid surface ocean on the planet that now stands as the hottest in our solar system. Picture this: early Venus, around 3.5 billion years ago, a world shrouded in clouds, not the sulfuric acid veil it bears today, but rather water clouds, white and billowing, reflecting the light of the young sun. Beneath the clouds, a warm surface, perhaps shallow seas, not as deep as Earth's oceans, but sufficient to fill basins and valleys with liquid water. The sky might have been predominantly overcast, with cloud cover thick enough to reflect sunlight and maintain moderate temperatures. The atmosphere would have been different: less carbon dioxide, more water vapor, possibly with nitrogen comprising a significant portion. It wouldn't have resembled Earth precisely. The continents, if they existed, would have had distinct shapes and compositions. Yet the essentials, liquid water, a stable atmosphere, a rocky surface, might have been strikingly similar. Some climate models suggest this state could have endured for an extraordinarily long period, potentially up to 2 billion years. If true, early Venus was habitable for roughly the same span that Earth has nurtured complex life. 2 billion years is ample time for microorganisms to evolve, diversify, and occupy every available niche. It is sufficient for an entire biosphere to emerge. While we lack evidence that this occurred, we also have no proof that it did not. The geological record has been obliterated. The oceans have vanished. Whatever life may have existed there, if life ever thrived, left no detectable trace for us to uncover. But where did the water go? The answer lies in a feedback loop so potent and irreversible that scientists have dubbed it with a name that echoes like a final judgment: the runaway greenhouse effect. Here's how it unfolds, step by step, akin to the chapters of a tragic tale. In the early days, Venus was a world adorned with water, perhaps shimmering on its surface, perhaps swirling in its atmosphere, or maybe both. The sun, in its youth, was a gentler luminary, casting a softer light that allowed for a stable, if not thriving, climate. But the sun, like all stars, does not remain in its dim phase indefinitely. Over the course of hundreds of millions of years, as hydrogen fuses into helium within its core, the sun gradually and inexorably becomes brighter, about 1% brighter every 100 million years. This change is imperceptible on the scale of human life, yet relentless when viewed through the lens of geological time. As the sun intensified, Venus began to heat up. Surface water started to evaporate at an accelerating pace. Water vapor is an exceptionally potent greenhouse gas, far more effective, molecule for molecule, than carbon dioxide at trapping infrared radiation. With each additional molecule of water vapor that entered the atmosphere, the heat trapped within increased, leading to even more evaporation, which in turn trapped even more heat. This created a positive feedback loop, a self-reinforcing system that magnifies its own alterations. On Earth, this feedback loop is kept in check. When evaporation reaches excessive levels, clouds begin to form. Clouds, being bright, reflect sunlight back into space, providing a cooling effect on the planet. Rainfall then removes water from the atmosphere, returning it to the surface. This system oscillates around an equilibrium, with the feedback loop present but under control. On Venus, however, there was no such control. At some point, though the exact timing remains a topic of debate, the feedback loop breached a critical threshold. The rate of evaporation outpaced any cooling mechanisms that could counteract it. Surface temperatures soared past the boiling point of water. If oceans existed, they began to boil, not gradually over millions of years, although the overall process may have spanned that time, but rather inexorably, with no mechanism to reverse the trend. Once water entered the atmosphere, its fate was sealed. In the upper reaches of Venus's atmosphere, above the protective cloud layers, ultraviolet radiation from the sun shattered water molecules. The liberated hydrogen atoms, light and energetic, escaped into the void of space. The oxygen, heavier and slower, lingered behind. But it did not accumulate. Instead, it was absorbed by the surface rocks, oxidizing the minerals that lay on Venus's surface. Over billions of years, nearly all of Venus's original water vanished. The hydrogen lost to the cosmos, the oxygen consumed by the rocks. The oceans evaporated, the water molecules were obliterated, and the hydrogen fled. Today, Venus is left with a meager atmosphere, containing only about 30 parts per million of water vapor at low altitudes, roughly 150,000 times less than what exists in similar layers of Earth's atmosphere. A 2024 study from the University of Cambridge suggested that Venus's interior is remarkably dry, far drier than Earth's mantle, implying that the planet may never have possessed enough internal water to support a significant surface ocean in the first place. This challenges the long-held belief that Venus harbored oceans for billions of years. The researchers proposed that the observed deuterium to hydrogen, D/H, enrichment could instead be maintained by a steady-state process, rather than necessitating a vast, ancient ocean. Yet, even under this new interpretation, it is clear that Venus lost whatever water it once had through atmospheric escape, and the mechanism, this runaway greenhouse effect, remains unchanged. Moreover, there was another factor amplifying this process: carbon dioxide. On Earth, carbon dioxide is continuously cycled between the atmosphere, oceans, and rocks through a process known as the carbonate-silicate cycle. Rainwater dissolves CO2 from the atmosphere, forming a weak acid that erodes silicate rocks. The dissolved carbon is then transported to the oceans, where it is incorporated into carbonate minerals and ultimately subducted into the mantle through plate tectonics. This cycle acts as a thermostat, regulating Earth's surface temperature over geological timescales. On Earth, this cycle has been functioning for at least 3.5 billion years. It has weathered ice ages, supervolcanic eruptions, mass extinctions, and asteroid collisions. It has maintained the planet's habitability through shifts in solar brightness, continental drift, and changes in atmospheric composition that would have spelled disaster without its presence. This cycle is arguably the most crucial process sustaining life on our planet. More vital than photosynthesis, more essential than the ozone layer, and even more significant than the magnetic field. Without the carbonate-silicate cycle, Earth would have succumbed to freezing or incineration long ago. In contrast, on Venus, the disappearance of water led to the breakdown of its thermostat. Without liquid water, rain ceased to fall. Without rain, there was no chemical weathering of silicate rocks. And without weathering, carbon dioxide could not be extracted from the atmosphere. Meanwhile, volcanic activity continued to release CO2 into the air, just as it does on Earth, but without any mechanism to remove it. The carbon dioxide began to accumulate, and accumulate, and accumulate. Today, Venus's atmosphere is composed of 96.5% carbon dioxide, with a total atmospheric mass approximately 90 times that of Earth's. The amount of carbon dioxide present in Venus's atmosphere is roughly equivalent to the total carbon stored in Earth's rocks and oceans. Carbon exists on both planets. On Earth, it is safely locked away in stone and sea. On Venus, it is all suspended in the atmosphere. To truly grasp the scale of this, consider a thought experiment. Imagine releasing every molecule of carbon dioxide sequestered in Earth's limestone, ocean sediments, coal deposits, oil reservoirs, and carbonate rocks. Every atom of carbon that has been meticulously stored over 4 billion years of geological and biological processes into the atmosphere all at once. The outcome would mirror that of Venus. Atmospheric pressure would surge, temperatures would soar, the oceans would evaporate. In a geologically brief moment, Earth could transform into a second Venus. This is not a mere prediction, it is a statement grounded in chemistry. The raw materials for a Venus-like atmosphere are present on Earth right now, locked within the rocks beneath our feet. The distinction between our sky and that of Venus lies not in composition, but in configuration. It's all about where the carbon resides. And on Venus, it resides in the most detrimental location possible. The greenhouse effect on Venus is so potent that it elevates surface temperatures by approximately 500 degrees Celsius compared to what they would be without an atmosphere. Earth's natural greenhouse effect raises surface temperatures by about 33 degrees, from a frigid -18 Celsius to a comfortable +15. Venus's greenhouse effect is 15 times more intense. It represents the most extreme greenhouse effect of any known planet, even surpassing the hot Jupiters that orbit closely to their stars, as those worlds are primarily heated by their proximity to their star rather than by atmospheric retention. On Venus, the atmosphere does the heavy lifting. The atmosphere serves as the furnace, and once that furnace was ignited, there was no way to extinguish it. This encapsulates the central tragedy of Venus's narrative. The same element, carbon, is present in similar quantities on both planets. The difference lies in its location. On Earth, geological and biological processes keep most of the carbon sequestered in solid form. On Venus, without water to facilitate the cycle, all of it has been released into the atmosphere, generating a greenhouse effect of such ferocity that the surface glows faintly in the dark. If you could somehow stand on the surface of Venus, shielded by an unimaginable suit of armor against the heat, pressure, and corrosive atmosphere, you would find yourself in one of the most bizarre environments in the solar system. The first thing that strikes you is the light, or rather, the lack of it. Despite being closer to the Sun than Earth, Venus's surface receives far less direct sunlight than you might anticipate. This is due to the thick layers of clouds overhead, which reflect and scatter the majority of incoming solar radiation. Instead of bright sunlight, the surface is bathed in a diffuse amber glow, reminiscent of an eternal, oppressive sunset. On a clear day on Earth, the illumination at the surface reaches about 100,000 lux. On Venus, however, it ranges from just 1,000 to 5,000 lux, akin to a heavily overcast day, but with an unsettling, monochromatic quality. Everything is shrouded in orange. The sky above you wouldn't be blue, it would present a deep yellow-orange hue, darkening to a brownish red at its zenith. The sun itself would be invisible, merely a brighter patch in the pervasive gloom. The clouds, composed of sulfuric acid droplets, float at altitudes between 48 and 70 kilometers above the surface, far above your head. Below these clouds, the atmosphere is surprisingly clear. No rain reaches the ground, as the sulfuric acid evaporates long before it can fall, in a phenomenon known as virga. Rain on Venus may fall, but it never lands. This fact is perhaps the most striking meteorological truth in the solar system. A world where acid rains from clouds that will never touch the surface. The sulfuric acid clouds are remarkable structures in their own right. Unlike terrestrial clouds, which are relatively thin, patchy, and fleeting, Venus's cloud layer forms a global, unbroken blanket, tens of kilometers thick, made up of multiple sublayers of sulfuric acid droplets of varying concentrations and sizes. The upper cloud layer, situated around 60 to 70 kilometers up, contains smaller droplets, while the middle and lower layers harbor larger droplets and more concentrated acid. Below approximately 48 kilometers, the atmosphere becomes too hot for sulfuric acid to remain in liquid form, causing the droplets to evaporate and release sulfuric acid vapor that eventually breaks down into sulfur dioxide and water vapor at even lower altitudes. The sulfur in these clouds originates from volcanic activity. Venus's volcanoes emit sulfur dioxide, SO2, into the atmosphere, where it reacts with trace amounts of water vapor and solar ultraviolet radiation to produce sulfuric acid. This process directly connects Venus's geological activity to its cloud chemistry. If volcanic activity were to halt, the sulfuric acid clouds would gradually thin and dissipate as the sulfur dioxide is depleted. The enduring presence of the cloud layer serves as evidence that Venus remains volcanically active. Somewhere beneath those clouds, magma continues to rise, gases are still venting, and the chemistry of destruction persists. These clouds also play a paradoxical role in Venus's energy dynamics. By reflecting 75% of incoming sunlight, they keep the surface dimmer than it would otherwise be. Without these clouds, Venus would absorb even more solar energy, leading to an even hotter surface. In a way, the clouds serve to temper the greenhouse effect. They are both a consequence of Venus's hostile chemistry and a partial safeguard against its most severe repercussions. Remove the clouds and conditions on Venus worsen. Retain the clouds and the sulfuric acid rain perpetually falls upward. There is no scenario in which Venus emerges victorious. The pressure here would be utterly overwhelming. At 92 atmospheres, the atmospheric pressure at Venus's surface is akin to being submerged in water at a depth of 900 meters. You wouldn't feel this as a constricting force. After all, pressure is uniform from all directions. But you would certainly perceive the air's extraordinary density. Sounds would travel in a peculiar manner, and visibility would be distorted due to the refractive bending of light in this thick atmosphere. If you were to drop a small object, it would descend more slowly than it would on Earth, buoyed by the heavy air. The density of Venus's near-surface atmosphere is approximately 6% that of liquid water, not quite a fluid, but significantly denser than any air we experience on Earth. You would sense its resistance with every movement. Your body, if exposed, would be compressed from all sides by a force equivalent to having the weight of a deep swimming pool pressing down on every square centimeter of your skin. No human-made structure designed for ordinary conditions could withstand such forces. Only steel pressure vessels, built for deep-sea submersibles, could maintain their integrity in such an environment. The atmospheric composition at the surface is dominated by carbon dioxide, 96.5%, alongside about 3.5% nitrogen and trace amounts of sulfur dioxide, argon, water vapor, carbon monoxide, helium, and other gases. At these extreme temperatures and pressures, carbon dioxide behaves not as a gas in the conventional sense, but as a supercritical fluid, a state of matter that exists above a substance's critical temperature and pressure, where the line between gas and liquid blurs. Venus's near-surface atmosphere exhibits characteristics of both. It flows like a gas, yet possesses the density of a liquid. Light refracts through it in strange ways, and convection operates differently than in any atmosphere on Earth. The temperature would be fatal beyond anything we experience on our planet. At a scorching 462 degrees Celsius, everything on Venus's surface exists in a state of thermal equilibrium. There's no cooling during the night, despite the fact that a single day on Venus is extraordinarily lengthy. Venus rotates so slowly that one complete day-night cycle takes 243 Earth days, longer than a Venusian year, which lasts only 225 Earth days. Moreover, Venus rotates in reverse, opposite to most planets. If you could glimpse the sun through the thick clouds, it would rise in the west and set in the east. This retrograde rotation may stem from a colossal impact early in Venus's history, or could be a result of tidal interactions between Venus's dense atmosphere and the Sun's gravitational pull. The exact cause remains a mystery. However, the implications are significant. Because of Venus's slow rotation, a single solar day, the time from one sunrise to the next, lasts about 117 Earth days. This means the day side of Venus is subjected to continuous heating for nearly 4 months, while the night side cools for the same duration. On a planet with a thinner atmosphere, this would create drastic temperature variations between day and night. Yet, Venus's atmosphere is so thick and adept at redistributing heat that the temperature difference between the day side and night side is virtually non-existent. The atmosphere functions as a colossal thermal blanket, leveling out all fluctuations. This thermal consistency extends across latitudes as well. On Earth, the equator is significantly warmer than the poles. On Venus, however, the surface temperature remains nearly uniform at every latitude. The entire planet is subjected to the same relentless heat, everywhere, at all times. There is no escape, no cooler sanctuary, no shadow to provide relief. The heat is absolute and inescapable. At the surface of Venus, the winds are surprisingly gentle. With minimal temperature differences to stir up significant air movement, these surface winds rarely surpass 1 meter per second, a soft breeze that would hardly register on Earth. Yet the thick atmosphere grants even these light winds an unexpected strength. The landscape bears the marks of this subtle force, with wind-sculpted features such as yardangs, wind streaks, and dune-like formations captured in Magellan radar images, showcasing how even the mildest breezes on Venus can shape its terrain over millions of years. The surface itself, unveiled by the Magellan radar orbiter in the early 1990s and the Soviet Venera landers, is predominantly characterized by expansive volcanic plains. Approximately 80% of Venus's surface is cloaked in smooth, basaltic lava fields, interspersed with towering volcanic structures. The Magellan mission, which orbited Venus from 1990 to 1994, mapped an astonishing 98% of the surface using synthetic aperture radar, a technique adept at piercing the dense cloud cover to reveal the ground below. The resulting maps unveiled a planet rich in geological diversity. Among the features are colossal shield volcanoes, some spanning hundreds of kilometers. There are coronae, circular or oval formations, typically 200 to 300 kilometers in diameter, created by the upwelling and eventual collapse of hot mantle material beneath the crust. Long, winding channels snake across the plains, some stretching thousands of kilometers, among the longest in the solar system, sculpted by flows of exceptionally low viscosity lava, possibly ultramafic lavas that are hotter and more fluid than any found on present-day Earth. Then there are pancake domes, flat-topped volcanic structures that have no earthly counterpart, formed when thick, viscous lava oozed through the crust and spread out before solidifying. Unique to Venus are the arachnoids, strange, spider-like formations with radiating fractures whose origins remain a topic of debate. Over 1,600 major volcanoes have been identified on Venus, surpassing any other planet in our solar system. Some of these giants, like Mart Mons, rise about 8 kilometers above the surrounding landscape, comparable in height to Earth's tallest volcanoes. However, the volcanism on Venus diverges significantly from that on Earth. Venus seems to lack plate tectonics, the system of rigid crustal plates that recycles Earth's surface through processes like subduction, spreading, and collision. Without this tectonic activity, Venus's internal heat cannot be released gradually and continuously through mid-ocean ridges and subduction zones. Instead, it accumulates over time, trapped beneath a stagnant crust. Some scientists propose that this built-up heat may be unleashed in catastrophic global volcanic resurfacing events, blanketing the entire planet in lava every few 100 million years. This hypothesis is supported by the uniform distribution of impact craters on Venus's surface, which suggests a planet-wide cleansing and reconstruction at roughly the same time, possibly between 300 to 700 million years ago. If this interpretation holds true, then Venus does not age in the same manner as Earth. Earth's surface is a patchwork of rocks of varying ages, from ancient cratons billions of years old to newly formed ocean floors. In stark contrast, Venus's surface may be uniformly young, with most of it dating back to the last major resurfacing event. The planet has effectively erased its geological history. Any records of Venus's early, potentially habitable era, any evidence of ancient oceans that might have once been etched in the rocks, have been buried beneath kilometers of lava. This is one of the most tragic chapters in the saga of Venus. Not only did this planet lose its ability to support life, but it also erased the traces of its once habitable past. Earth boasts ancient rocks nearly 4 billion years old, rich with chemical signatures of primordial oceans and even fossilized microorganisms. Mars, too, holds the remnants of riverbeds, lake basins, and mineral deposits that tell a compelling story of a wetter era. Yet Venus, through its own volcanic fury, has obliterated much of the physical evidence that could reveal what it was like before the greenhouse effect took over. Most of this evidence is gone, but perhaps not all of it. The tesserae, those mysterious highlands of twisted and folded terrain, predate the last global resurfacing event. They stand as the survivors, the witnesses to a different era. These ancient formations may still harbor the chemical and mineralogical signatures of a different Venus, a Venus where water once flowed. The volcanic activity on Venus may not be a relic of the past. In 2023 and 2024, analysis of archival data from the Magellan Radar Orbiter unveiled signs of recent volcanic eruptions, changes in surface features between radar images taken just months apart in the early 1990s. One volcanic vent appeared to have expanded significantly between observations, suggesting an active lava flow. If this is confirmed, Venus would join the ranks of only 3 bodies in the inner solar system known to exhibit present-day volcanism, alongside Earth and Jupiter's moon Io. Active volcanism on Venus carries profound implications. It indicates that the planet's interior remains hot, still convecting, and still releasing gases into the atmosphere. It suggests that carbon dioxide and sulfur dioxide continue to be expelled into the air through volcanic vents. Furthermore, it implies that the geological engine that transformed Venus from a potentially habitable world into a hellish landscape may still be operational, a machine that began its relentless work billions of years ago and has never ceased. Beneath that lava, beneath the crust, lies Venus's interior, a realm shrouded in intense speculation and nearly devoid of direct data. We have yet to measure a seismic wave on Venus. We have never penetrated its subsurface. The only insights into its internal structure come from gravity measurements, theoretical models, and the simple observation that Venus is roughly the same size and density as Earth, suggesting a similar composition, an iron-nickel core enveloped by a silicate mantle. However, Venus lacks a global magnetic field. Earth's magnetic field is generated by convection currents in its liquid iron outer core, a dynamo fueled by the cooling and solidification of the inner core. Venus, despite having a core of comparable size, produces no detectable global field. Why is that? The answer remains elusive, but one possibility is that Venus's core has cooled too slowly, or not at all, to create the convection necessary for a dynamo. Without plate tectonics to efficiently transport heat from the interior, Venus's core may remain entirely liquid, lacking the partial solidification that drives Earth's dynamo. Alternatively, it could be that the core has cooled so thoroughly that it is completely solid, effectively shutting down the dynamo from the other end. Regardless of the reason, the outcome is the same. Venus lacks a magnetic shield. The solar wind directly interacts with Venus's upper atmosphere, stripping away light atoms, including whatever remnants of water Venus still possesses. The absence of a magnetic field did not directly cause Venus's water loss. The runaway greenhouse effect was the primary culprit, but it certainly accelerated the process. Without a magnetosphere, the upper atmosphere is exposed to the relentless assault of the solar wind, which continuously erodes the lightest atmospheric components. While Venus does have a weak, induced magnetic field, generated by the interaction between the solar wind and the planet's ionosphere, this offers far less protection than a true, internally generated dipole field. The implications of this exposure are tangible, not just theoretical. The Venus Express orbiter has observed streams of hydrogen and oxygen ions escaping from the night side of Venus, whisked away by the solar wind. The ratio of escaping hydrogen to oxygen stands at approximately 2:1, precisely what one would anticipate from the breakdown of water molecules. Venus is shedding water in real time, molecule by molecule, split by sunlight and swept away by the solar wind. This process has persisted for billions of years and will continue until the last vestiges of water vapor disappear. So how much water is left? A mere fraction. The current atmosphere harbors only about 30 parts per million of water vapor near the surface, roughly 100,000 times less than Earth's atmosphere at similar altitudes. If all the water in Venus's atmosphere were to condense onto the surface, it would create a global layer merely 3 centimeters deep. In contrast, if Earth's oceans were evenly distributed, they would cover the planet to a depth of about 2,700 meters. Venus has nearly exhausted its water supply. What little remains is but a trace, a spectre, a final whisper of oceans that vanished billions of years ago. Even now, spacecraft continue to detect hydrogen and oxygen ions escaping from Venus's upper atmosphere in a ratio consistent with the ongoing breakdown and loss of water molecules. Venus is still losing water, drop by drop, atom by atom. What little is left is being gradually stripped away into the void of space. Amidst all this evidence of desolation, there lingers a suggestion of something more, something that defies complete explanation. In September 2020, a team of astronomers led by Jane Greaves from Cardiff University announced the detection of phosphine, pH3, in the cloud layer of Venus at altitudes around 55 kilometers above the surface. This detection was made using spectroscopic observations from the James Clerk Maxwell Telescope in Hawaii and the Atacama Large Millimeter Array in Chile. The reported abundance was approximately 20 parts per billion, a minuscule amount, yet profoundly perplexing. Phosphine is noteworthy because, on Earth, it is produced almost exclusively through biological processes, specifically by anaerobic microorganisms that reduce phosphate in oxygen-poor environments. It can be found in swamps, within the intestines of animals, and in certain industrial processes. In the oxygen-rich atmosphere of a rocky planet, phosphine is thermodynamically unstable. It should be rapidly destroyed by oxidation. Its presence necessitates a continuous source. On the gas giants Jupiter and Saturn, phosphine is generated deep within the atmosphere through high-pressure chemistry and brought to the surface by convection. However, on a rocky planet like Venus, where the atmosphere is predominantly oxidizing, no known abiotic chemical process can generate phosphine in the quantities reported. The announcement sparked immense excitement and significant controversy. Within weeks, other research teams contested the findings, arguing that the spectral signal attributed to phosphine could instead be due to sulfur dioxide, a common and well-understood component of Venus's atmosphere. subsequent observations from other telescopes failed to replicate the detection. The debate grew heated, personal, and at times quite acrimonious. Yet, the narrative did not conclude with the controversy. In 2024, Greaves' team released new data from the Atacama Array, utilizing additional observations and refined analytical techniques. The new results once again indicated the presence of phosphine, and this time the researchers contended they could eliminate sulfur dioxide as a contaminant. They also uncovered tentative evidence of ammonia, another gas that, in Venus's hyperacidic atmosphere, poses a challenge to explain through known chemistry. Ammonia is intriguing because, if it exists, it could neutralize the sulfuric acid in the cloud droplets, creating conditions far more conducive to organic chemistry than pure sulfuric acid. Meanwhile, Rakesh Moghul at California State Polytechnic University revisited data from NASA's Pioneer Venus probe, which entered the planet's atmosphere back in 1978. He uncovered signs of phosphine in the deep cloud layer, with concentrations aligning with more recent findings. Remarkably, this data had been tucked away in archives for over 40 years, unnoticed. In a parallel line of inquiry, scientists at MIT explored whether the fundamental building blocks of life, amino acids, could endure in concentrated sulfuric acid at levels akin to those in Venus's clouds. To their astonishment, they discovered that 19 amino acids remained stable for up to 4 weeks. The molecular structure of these life-building blocks held firm. It turns out that sulfuric acid isn't the universal solvent we once thought. Some of the chemistry essential for life might just be feasible, even in the harshest conditions Venus has to offer. However, none of this definitively proves that life exists on Venus. The detection of phosphine is still a matter of debate. The ammonia findings are tentative at best. The amino acid stability tests were conducted under laboratory conditions, not in the actual clouds of Venus. Moreover, alternative explanations, such as unknown photochemical processes, volcanic activity, or reactions involving dust particles, could potentially generate phosphine without any biological involvement. In 2024, a new abiotic pathway was suggested, a photochemical process where ultraviolet radiation catalyzes reactions on acidic mineral dust particles in Venus's upper atmosphere, possibly generating phosphine without any biological input. If validated, this pathway would challenge the case for a biological origin. Yet it remains to be experimentally confirmed, and its predicted phosphine output has yet to align with the observed concentrations. The phosphine debate highlights a more profound issue. Our understanding of Venus's atmospheric chemistry is insufficient to confidently determine what should or shouldn't be present. If we struggle to predict the chemical makeup of our nearest planetary neighbor, how can we hope to interpret the atmospheres of exoplanets located hundreds of light-years away? The discovery of phosphine, whether of biological origin or not, has exposed the extent of our ignorance regarding Venus's chemistry. And in science, ignorance is not a failure. It represents a frontier waiting to be explored. Yet, the possibility of life has not been dismissed. The very fact that we cannot categorically assert, "No, this is definitely not life," is a striking testament to the limits of our understanding. The cloud layer of Venus, situated between approximately 48 and 60 kilometers above the surface, stands out as one of the most fascinating environments in our solar system. At these altitudes, temperatures fluctuate between about 0 and 60 degrees Celsius, comfortably within the range that extremophile microorganisms on Earth can endure. The pressure is roughly 1 atmosphere, comparable to sea level on Earth. There exists liquid, sulfuric acid droplets, yes, but liquid nonetheless. There is energy, sunlight filtering through above the clouds, chemical energy swirling within them. Carbon dioxide, nitrogen, and trace amounts of water vapor and sulfur compounds could potentially serve as metabolic substrates. If microorganisms inhabit Venus's clouds, they would confront extraordinary challenges: extreme acidity, a lack of solid surfaces, and the relentless cycling of cloud droplets that eventually evaporate and reform. However, extremophiles on Earth have demonstrated that life is far more resilient and inventive than we once thought. Organisms flourish in boiling water, concentrated acid, the crushing depths of the ocean, and the radiation-laden ice of Antarctica. The real question isn't whether life could endure some of the conditions in Venus's clouds, it's whether the specific combination of factors there, hyperacidity, water scarcity, and atmospheric cycling, crosses a threshold that no form of biology can withstand. There exists a hypothesis, speculative yet scientifically grounded, regarding the potential for life to thrive in the clouds of Venus. Proposed by Sarah Seeger from MIT and her colleagues, this model imagines microorganisms residing within sulfuric acid droplets, safeguarded by an internal buffering chemistry that maintains a neutral pH within their cell membranes. As these droplets grow and eventually descend below the cloud layer, the organisms would undergo desiccation, transforming into dormant spores that drift down into the scorching lower atmosphere. Eventually, convective updrafts would lift the spores back into the cloud layer, where they would rehydrate, reactivate, and begin to reproduce once more. A continuous cycle of growth, dormancy, and resuspension. While this life cycle has no direct counterpart on Earth, its individual elements, desiccation tolerance, spore formation, and atmospheric transport, are well documented in terrestrial biology. Microorganisms can be found in Earth's stratosphere, transported there by convection and volcanic activity. Some endure the harsh ultraviolet radiation and extreme cold of the upper atmosphere for extended periods. The pressing question is whether a similar mechanism could sustain a self-replicating population within the clouds of Venus over geological timescales. If life indeed exists in the clouds of Venus, it would signify something extraordinary. A biosphere without a solid surface, ocean or soil. A biosphere entirely suspended in the atmosphere of a dying world, surviving in the last habitable niche that the planet has to offer. It would be, in the most literal sense, life on the brink. We do not know, and we will not know until we venture there and observe. The narrative of Venus is also a narrative about Earth, about what our planet might one day become. This comparison is unsettling, and rightly so. Venus and Earth began as twins. They formed from the same cosmic material, occupying adjacent orbits within the habitable zone of the same star. For perhaps the first 2 billion years of their existence, they may have been broadly similar. Rocky worlds with atmospheres, volcanic activity, and possibly even liquid water. Then, at some pivotal moment, their paths diverged irrevocably. One remained habitable, the other ignited into a furnace. The difference was subtle. It was not the result of a collision with a rogue planet, a nearby supernova, or some cosmic disaster. It was merely a few % more solar radiation, a slightly closer orbit. A feedback loop that, on one planet, remained balanced, while on the other spiraled into chaos. On Earth, the carbon cycle functions as a thermostat. When the planet warms, the chemical weathering of rocks accelerates, drawing more carbon dioxide from the atmosphere and cooling the planet. Conversely, when the planet cools, weathering slows, and volcanic CO2 accumulates, warming it again. This negative feedback loop has maintained Earth's temperature within the range necessary for liquid water for most of the last 4 billion years. It is not flawless. There have been ice ages and periods of extreme warmth, but it has never failed catastrophically. On Venus, the thermostat malfunctioned, and the malfunction was permanent. Once the water vanished, the carbon cycle could not restart. The planet became locked in a new state, a hot, arid, CO2-dominated greenhouse from which there is no natural escape. Could this fate befall Earth? Not within any time frame relevant to human civilization as a result of human-induced climate change. The physics of a runaway greenhouse effect demands significantly more solar radiation than than Earth currently receives. By most estimates, Earth would need to warm by hundreds of degrees before crossing the runaway threshold, something not expected to happen for roughly 1 billion years as the Sun gradually brightens. Long before that, the slow evaporation of Earth's oceans will extinguish life as we know it. But this process will unfold over hundreds of millions of years. Venus serves as a powerful reminder that a planet's ability to support life is not a given. It's not a static state, rather, it's a fragile, ever-shifting balance, an intricate dance between the energy it absorbs and the energy it radiates, between carbon released and carbon captured, between water that evaporates and water that returns. Venus illustrates the consequences of this balance tipping too far, not in some abstract theoretical way, but in tangible physical reality on a planet that shines brightly in our evening sky. The takeaway isn't that Earth is destined to become Venus overnight. The real lesson is that planets can perish, worlds can lose their oceans, atmospheres can become so saturated with heat that their surfaces become uninhabitable. This has occurred at least once in our own solar system, to a planet strikingly similar to ours. Venus is not merely a metaphor, it is a critical data point, the most sobering one in the realm of planetary science. Moreover, this data point resonates far beyond our solar system. As astronomers uncover rocky planets nestled in the habitable zones of distant stars, they confront a fundamental question. How many of these planets are Earth-like, and how many resemble Venus? A planet residing in the habitable zone, the region around a star where liquid water could theoretically exist on a rocky surface, doesn't automatically guarantee habitability. Venus lies within the inner edge of our Sun's habitable zone. It receives the right amount of energy, possesses the right size, the right composition, and the right ingredients. Yet it is a scorching furnace. When the James Webb Space Telescope and its successors embark on the task of characterizing the atmospheres of rocky exoplanets, detecting carbon dioxide, water vapor, methane, and oxygen, they must differentiate between vibrant worlds and lifeless ones. A dense carbon dioxide atmosphere on a rocky planet within the habitable zone could indicate a flourishing carbon cycle, complete with oceans and continents. Alternatively, it might signal a runaway greenhouse effect, an airless ocean, a Venus. The distinction between paradise and purgatory may be subtle. Without a deep understanding of Venus, without clarity on how and when the runaway greenhouse effect began and what warning signs accompanied it, we may struggle to interpret these signals accurately. Venus is not just an intriguing subject, it is essential. It serves as the control experiment, the path not taken, the alternate outcome. Without Venus, our comprehension of planetary habitability remains incomplete. With Venus, it is at least candidly uncertain. Studying Venus transcends mere planetary science. It encompasses astrobiology and climate science. It delves into what makes a world worth inhabiting and what can strip that away. Take, for instance, the exoplanet TRAPPIST-1, a system of 7 rocky planets orbiting a dim red dwarf star approximately 40 light-years from Earth. Several of these planets reside in the habitable zone. Astronomers are utilizing the James Webb Space Telescope to scrutinize their atmospheres. But what will they uncover? If one of these planets boasts a thick carbon dioxide atmosphere, does that imply it is a Venus, a lifeless world scorched by a runaway greenhouse effect? Or could it signify a young Earth, a planet where the carbon cycle is vibrant, where oceans and continents coexist, where life might be taking its first tentative steps? The answer hinges on our understanding of the boundary between Earth-like and Venus-like outcomes. And we cannot grasp that boundary without comprehending Venus itself, without knowing precisely when and how the shift from habitable to hellish occurred, and what factors dictated the outcome. Venus is not merely a planet. It is a template, a calibration standard for the entire field of exoplanetary science. Without it, We are interpreting spectral data blindly, unable to distinguish between the signatures of life and those of death. This is precisely why the forthcoming missions to Venus hold such immense significance. They are not simply ventures to a neighboring planet. They are the foundation upon which we will construct the interpretive framework necessary to analyze the atmospheres of exoplanets, worlds orbiting distant stars that we may never set foot on, but can only study through the faintest glimmers of starlight filtered through their alien atmospheres. Venus serves as our Rosetta Stone, and we have only just begun to unlock its secrets. Yet, for all its significance, Venus remains one of the least explored planets in our solar system. The contrast with Mars is striking. NASA has dispatched a multitude of rovers, landers, orbiters, and even helicopter drones to the Red Planet. For decades, we have navigated robotic explorers across its surface, drilling into its rocks, analyzing its soil, capturing breathtaking images of its sunsets, and recording the haunting sound of winds sweeping through its craters. We are actively planning missions to return Martian samples to Earth for further study. In stark contrast, we have sent almost nothing to Venus in the past 40 years. The last spacecraft to operate on Venus's surface was the Soviet Vega 2 lander, which touched down in 1985. The last dedicated orbiter sent by the United States, Magellan, arrived in 1990 and utilized radar technology to create the first high-resolution global map of Venus's surface before it was deliberately plunged into the atmosphere in 1994. The European Space Agency's Venus Express orbited the planet from 2006 to 2014, meticulously studying its atmosphere and climate. Japan's Akatsuki orbiter has been observing the dynamics of Venus's atmosphere since 2015. What both Akatsuki and Venus Express have unveiled is an atmosphere of remarkable complexity, a realm where, despite the near-total absence of weather at the surface, the upper atmosphere functions as a dynamic engine of global circulation. Venus's atmosphere showcases a phenomenon known as superrotation. The entire upper atmosphere completes a full circuit around the planet in about 4 Earth days, approximately 60 times faster than the planet itself rotates beneath it. Winds at the tops of the clouds reach speeds of 360 kilometers per hour, far exceeding the sluggish surface winds recorded by the Venera landers. This superrotation stands as one of the great unsolved enigmas of atmospheric science. On Earth, the atmosphere rotates at roughly the same speed as the surface, driven by differential solar heating and the Coriolis effect. On Venus, however, the atmosphere has somehow been accelerated to speeds that far surpass the planet's own rotation. The source of energy for this acceleration, as well as the mechanism that sustains it against friction, remains poorly understood. The clouds of Venus are stratified. The primary cloud layer, composed of sulfuric acid droplets, stretches from approximately 48 to 70 kilometers above the surface. Above this cloud layer, the atmosphere is relatively clear. Below it, the conditions are also clear, but hot, dense, and oppressively dark. This cloud layer serves as a boundary between two distinct worlds: the relatively cool, dynamic upper atmosphere and the hot, stagnant lower atmosphere. Between these two realms, within the cloud deck itself, lie enigmatic dark patches that absorb ultraviolet light. First observed decades ago, these patches change in shape and intensity over time, and their composition remains a mystery. Some researchers speculate that these UV-absorbing entities could be biological, populations of microorganisms containing pigments that absorb ultraviolet radiation for protection or photosynthesis. Others propose that sulfur compounds or iron chloride minerals could account for the absorption without invoking biological explanations. The debate continues, unresolved. Venus's atmosphere is a realm of enigmas, shrouded in mysteries that current missions are ill-equipped to unravel. The chemistry of the lower atmosphere, beneath 30 kilometers, remains uncharted territory, untouched by any spacecraft. The night-side atmosphere has only been glimpsed from orbit, while the deep troposphere, the zone between the surface and the cloud base, represents a vast void in our understanding. We are largely in the dark about the chemical makeup below 30 kilometers. The precise levels of water vapor at various altitudes elude us. The vertical distribution of sulfur compounds is still a mystery. We cannot confirm whether trace gases like carbon monoxide, hydrogen sulfide, or carbonyl sulfide behave according to our theoretical models. In fact, the deep atmosphere of Venus stands as the largest unexplored chemical reservoir among the planets of the inner solar system. Enter Da Vinci's descent probe, poised to transform our understanding. As it descends through the atmosphere over approximately an hour, it will continuously sample the air, measuring noble gas isotopes that provide clues about Venus's formation, trace gases that illuminate the planet's chemical state, and the vertical profiles of water vapor and sulfur compounds crucial for deciphering the climate system. This mission promises the most thorough atmospheric analysis ever conducted at Venus and marks the first direct sampling of its deep atmosphere since the Soviet Vega probes in 1985. While the probe isn't designed to survive a landing, there exists a slim, unforeseen possibility that it might. Should it land gently on sufficiently flat terrain, its instruments could continue to function for up to 18 minutes in the searing conditions of Venus. 18 minutes on the surface of the most inhospitable world in the inner solar system may seem trivial. Yet, Venera 7 managed to transmit data for 23 minutes, and those fleeting moments revolutionized our understanding of Venus. To fill in the gaps in our knowledge, we will need not only orbiters, but also probes, balloons, and potentially long-lasting surface stations capable of enduring the extreme environment of Venus. However, no spacecraft has ventured into Venus's atmosphere since 1985, nor has any touched its surface since then. The last color photographs captured from the surface date back to 1982. This status quo is on the brink of change. A new wave of Venus missions is in the works, pending funding and political support, that promises to be the most extensive investigation of Venus in the annals of space exploration. NASA's Da Vinci mission, Deep Atmosphere Venus Investigation of Noble Gases, Chemistry and Imaging, is set to deploy a spherical probe through Venus's atmosphere, descending through the cloud layer into the deep atmosphere below, with an unprecedented level of chemical analysis. The probe will scrutinize noble gases and their isotopes, which hold the keys to understanding how the atmosphere formed and evolved, while capturing high-resolution images of the tesserae, Venus's oldest and most geologically intricate terrain, during its descent. Da Vinci aims for a launch in late 2030, with the probe entering Venus's atmosphere in early 2033. Meanwhile, NASA's Veritas mission, Venus Emissivity, Radioscience, INSAR, Topography, and Spectroscopy will orbit Venus, employing radar to map the surface with resolutions far superior to those achieved by Magellan, creating three-dimensional topographic maps that could unveil active volcanism, tectonic activity, and surface alterations. Its launch is slated for no earlier than 2031, though its future hangs in the balance amid budgetary constraints. The European Space Agency's Envision orbiter, selected in 2021 and formally adopted in 2024, will investigate Venus from the inside out, exploring the connections between its geological activity, surface composition, and atmospheric chemistry. Envision is equipped with a subsurface radar sounder that will probe beneath Venus's surface for the first time, potentially uncovering hidden geological structures and remnants of its ancient past. The launch is targeted for November 2031. Together, these three missions, if all goes according to plan, will usher in a decade of Venus, potentially revolutionizing our comprehension of this enigmatic planet. However, they are not without their hurdles. Budget cuts to NASA's science initiatives have cast a shadow over both Da Vinci and Veritas. The political climate surrounding science funding remains precarious. Moreover, the engineering challenges posed by Venus's extreme environment are daunting. The searing heat, crushing pressure, corrosive atmosphere, and the opacity that shrouds most wavelengths of light. Even if all 3 missions launch as scheduled, the data they gather will require years of meticulous analysis. The answers to our most profound inquiries: did Venus ever host oceans? Is there life lurking in its clouds? What accounts for Venus's lack of a magnetic field? When did the runaway greenhouse effect begin? May not be fully unveiled by a single generation of missions. Grasping the complexities of Venus will demand patience, ongoing investment, and a readiness to face potentially unsettling truths. For the uncomfortable reality about Venus is that it is not an alien realm. It is, in fact, a familiar one. It represents what a habitable planet may resemble when things go awry. There is yet another aspect of Venus that merits our attention, as it links the planet's past to its most ancient and enigmatic landscapes. The tesserae are regions of intricately deformed, complex, interlocking terrain that cover about 7% of Venus's surface. They are the oldest geological features visible on the planet, predating the extensive volcanic resurfacing that cloaked most of Venus in lava. The tesserae endured this resurfacing, standing as ancient rock islands amidst the younger volcanic plains. The tesserae hold scientific significance because they may harbor clues about Venus's earliest geological history, including potentially the era when the planet may have had surface water. Some researchers interpret the layered, valley-cut terrain of the tesserae as indicative of water erosion, akin to river valleys on Earth. If this interpretation holds true, then the tesserae represent Venus's closest geological memory of its habitable past. Da Vinci is specifically engineered to photograph the tesserae during its descent, capturing high-resolution images that could determine whether these formations were indeed sculpted by flowing water. Veritas and Envision will map the tesserae from orbit, detailing their composition and topography. If the tesserae contain minerals that could only have formed in the presence of liquid water, such as granites, which on Earth require water-rich magmas, then the case for a wet Venus would be significantly bolstered. The tesserae derive their name from the Greek word for tiles, a nod to their blocky, interlocking appearance in radar imagery. They exhibit extensive deformation, with multiple sets of fractures, folds, and ridges intersecting at various angles, suggesting a complex history of compression and extension. Some tesserae rise several kilometers above the surrounding plains, forming elevated plateaus. Others appear as isolated blocks encircled by younger lava flows, resembling islands in a frozen ocean. The composition of the tesserae is one of the most pressing questions in Venusian science. On Earth, different rock types form under distinct conditions. Basalt emerges from eruptions at mid-ocean ridges and volcanic hotspots. It is dark, dense, and rich in iron. Granite, on the other hand, forms in the presence of water. Its creation necessitates water-rich magmas that partially melt continental crust. If the tesserae are found to be granitic in composition, it would provide compelling evidence that Venus once had liquid water on its surface, as granite cannot form without it. Tantalizing clues beckon us from the depths of Venus. Near-infrared observations from orbit have uncovered emissivity anomalies in certain tessera regions, hinting at compositions akin to felsic, granite-like materials rather than the basaltic compositions that dominate the volcanic plains. However, these measurements are indirect, filtered through the planet's dense atmosphere, leaving room for uncertainty in interpretation. Upcoming missions like Veritas and Envision promise to measure these emissivity signatures with unprecedented precision and spatial resolution, potentially providing definitive answers. Yet, the intrigue doesn't end there. What secrets lie beneath the tesserae? Envision's subsurface radar sounder, the first of its kind ever dispatched to Venus, is set to delve as deep as 1 kilometer below the surface. If ancient riverbeds, lake beds, or other water-carved features are hidden beneath the lava plains, the radar may reveal them. It's akin to conducting an archaeological dig on a planetary scale, unearthing the buried history of a world that has endeavored to erase its own past. The tesserae stand as Venus's oldest surviving witnesses, potentially holding the key to one of the most profound questions about the planet. Did Venus ever truly harbor life? Now let's step back from the intricate chemical ratios, mission timelines, and atmospheric pressures and contemplate the significance of Venus. Here is a planet that formed alongside Earth, from the same primordial cloud, at the same moment, from the same cosmic dust. A world that may have once experienced rain, rivers, and the serene reflection of clouds on tranquil waters. For over 1 billion years, conditions might have been gentle enough for life to emerge and thrive. And then, through a process as gradual and relentless as the slow brightening of a star, it lost everything. The water boiled away, hydrogen escaped into space, carbon was released, the thermostat failed. What remained was a hellscape that has endured far longer than any civilization on Earth has existed. Venus did not meet its end in a cataclysmic event. It succumbed slowly, in stages, through a process that began so subtly that, had anyone been there to witness it, they might not have noticed for millions of years. The warming would have been gradual. Droughts would have been sporadic. Storms would have intensified, then calmed, only to intensify again. The oceans would have receded, the shores would have retreated, and by the time the trend became undeniable, it would have been too late to reverse. This is the tragedy of Venus. Not that it perished violently, but that it faded quietly. Not that it was obliterated from the outside, but that it was consumed from within. By the same physical laws that allow Earth to thrive, operating at a slightly different intensity, in a slightly different location, with a slightly different outcome. And somewhere, high in the clouds of this desolate world, something may be producing a gas that defies all known, non-biological explanations. Something may be altering the chemistry of the cloud droplets in ways that render them less acidic, more conducive to organic molecules, more welcoming to something that might, against all odds, be alive. We do not know. The data is ambiguous. The detections are disputed. Alternative explanations abound. Yet the question remains open, and the question itself, is there life on Venus, stands among the most extraordinary inquiries that science has ever earnestly posed about a world beyond our own. To find an answer, we must venture there. We must send probes into those clouds, sample the droplets, analyze the chemistry, and search for the unmistakable signatures of life, or the undeniable absence of them. And we must approach our findings with honesty, whether they affirm our hopes or shatter them. Venus is far from finished with its revelations. For 4.5 billion years, it has shrouded its mysteries behind a thick veil of clouds, eluding the gaze of every telescope, too scorching for any lander, and too inhospitable for every orbiter that dared to linger. But now, we are on the brink of a return. For the first time in 40 years, spacecraft will plunge into that atmosphere, navigate through those clouds, and sample that air. What they uncover will transform our understanding of our own planet, redefine the limits of life, and illuminate the delicate, transient nature of every habitable world in the cosmos. Venus does not exist in a vacuum. It belongs to a vast array of rocky planets residing in habitable zones around distant stars. Planets we are uncovering by the thousands, whose atmospheres we are just beginning to analyze. Among them, there are surely other Venuses, other worlds that once brimmed with oceans and lost them, other realms where the greenhouse effect spiraled out of control, other planets that succumbed to their own fates. By deciphering Venus, we gain insight into a category of planetary demise. Misunderstanding it could lead us to misinterpret the destinies of countless worlds scattered across the galaxy. The implications extend far beyond our own backyard. They are cosmic in scale. And there it is, a beacon in the evening sky, visible to the naked eye, shining brighter than any star. A point of white light poised near the horizon, stunning, recognizable, named after the goddess of love. It carries the tale of a world that lost its water, its oceans, its opportunities, yet perhaps, against all odds, managed to preserve something small and resilient in the last habitable niche it has left. Venus, our closest neighbor, our twin in the cosmos, continues to rotate slowly in reverse beneath its cloud cover. Still hot, still silent, still awaiting someone to come and decipher the message it has borne for 4 billion years. The solar system offers 2 case studies in planetary habitability. One thrived, the other faltered. They orbit the same star, a mere 30% apart, nearly identical in size and composition. One boasts oceans, forests, cities, and 7 billion human minds pondering the universe. The other is cloaked in sulfuric acid clouds, with surface temperatures hot enough to melt tin, and, perhaps, a few molecules of phosphine wafting through its atmosphere, generated by a process that remains a mystery. The chasm between paradise and desolation is not vast. It spans just 42 million kilometers, a rounding error in the grand scheme of the galaxy, a difference so minuscule that an alien astronomer, observing our solar system from 100 light-years away, might struggle to discern which of the 2 planets is alive and which is lifeless, unless they examined very, very closely. And therein lies the ultimate lesson of Venus. Habitability is not an inherent right. It is not a permanent condition. It is a state that must be sustained. By the right distance from a star, by the right amount of water, by the right chemical cycles, by the right blend of geology, biology, and sheer luck. Venus possessed many of these elements, not all of them, and certainly not indefinitely. Every evening, as Venus graces the western sky after sunset, it silently transmits this message across 42 million kilometers of space. A message inscribed in deuterium and carbon dioxide, in sulfuric acid and basalt, in the quiet of a world that once may have known the touch of rain. 4 billion years ago, Venus and Earth were neighbors in a nascent solar system. Both had atmospheres, both had warmth, both may have had water, and then one of them lost it all. Not through external catastrophe, but through internal chemistry, through the slow, relentless, irreversible build-up of consequences. We spotted Venus in the heavens long before we ever glimpsed it through a telescope. We bestowed a name upon it before we truly grasped its nature. We envisioned lush jungles and vast oceans hidden beneath its shrouded clouds, long before we sent our first probe hurtling into its searing atmosphere. Yet, when the reality was unveiled, when we recorded temperatures soaring to 860 degrees Fahrenheit, when the pressure readings indicated a staggering 90 atmospheres, when the deuterium ratio narrated the tale of an ocean that once existed but evaporated into the void of space, the truth proved to be far more complex and significant than any dream we had conjured. And the more attentively we listen, the more secrets it unfolds.